In this problem, we are given two binary trees and we have to return whether they are equal or not. And by equal, we mean they should be structurally equal. And here if you see these two trees, they are structurally same. This one has left and right, and this one has left, right. So they have exact same structure, but that is not enough. We have to check the values also. So 5 is equal to 5, 3 is equal to 3, 6, 6. So if we flip one of these, so 4 comes here, 2 goes here. Structurally they will be same, but the left of 3 will hold a value of 4 if we flip it. But on this side, it's 2. So that ordering is also important. It should be exactly same. So we will see a recursive and iterative solution for this. The recursive solution would be an easy solution, and it will be the preferred way of solving it unless you are asked to solve it iteratively. The iterative version would be a bit difficult compared to the recursive version. And this recursive version will be very simple, and you can write it in 3 lines of code. You can even merge them into 1 line of code if you combine different conditions. And in this iterative approach, we will take the hint of breadth first traversal of graphs. We will do it in level order fashion, but it will be quite some amount of modification will be required into a normal BFS. So it will be a bit tougher than that normal BFS. So we will see what are the differences. First, let's look at the recursive way of solving it. So clearly you will first compare their roots. So when you are given a function, you are given a tree node. You are given 2 pointers, tree node P and tree node Q. So first thing is that you are given the roots. So first roots should be same. So if one of them is null, better both be null, otherwise we will return false. So if both are null, then it's fine, both are equal, both trees are empty. So if P is equal to null and Q is equal to null, then return true. If one of them is not null, or one of them is null, or Q is null, then return false. So if both are null, it will return from here itself. So it proceeded here, that means both are not null. But if one of them is null, then that means other is not null, because both cannot be null here. If both were null, we would have returned from here. So in this case, we return false. And now in the next line, it means that both are not null. If any of them are null or both are null, it would have already returned before coming to this line. So here we are sure that both are not null, so we will check their values. So if p.val, or in C++ it will be this arrow, is not equal to q.val, then return false. Otherwise this root is same. Now what we need to do, we will check for this left subtree. So if the complete trees are same, then this left subtree should also be same as this left subtree, and this right subtree should be same as this right subtree. So if it's valid till this point, it has not returned from here. That means here it's fine, for the root it's fine. So we return whatever is this function, I am calling it f, return f, p left, q left. So that will check if this subtree is same as this, and the same function p right, q right, and we are done. So what this function will do, again recursively call on this and this. So first it will match the root. If they are same, it will recursively call on this and this, and similarly on this and this. So when it's called for 2 and 2, it will check roots are same, the value is also same, both are not null. So it will call for its left and this left. So both are null. So it will come here and it will return true. So this will return true to the calling function. This will return true to its calling function, and it will come back to 2, and these are already same. So ultimately it will return true to this part 3. Similarly 4 will also return true, and finally 3 will return true, and 6 will return true. So this will return true, this will also return true. So true and true means true. So in this case, true will be returned. Now let's see how we will solve it iteratively. So if you are not familiar with breadth first traversal, better to review BFS video and see how we can use a queue to do breadth first traversal, or if it's a tree, we would do it level order traversal. So first root is visited, then next level, and so on. So once you are familiar with BFS, you are good to go. So there are some subtle differences from normal BFS. One definitely is that here we are doing BFS in two trees or two graphs simultaneously in parallel. In normal BFS, we are just having one queue, we are doing one BFS. So we have one queue for this one, let's call it Q1, let's call it Q2. So what we do, we again do the same check, compare if we have to add these checks, that if one is null, others should also be null. If only one of them is null, return false. If their values are same, then we are good to go. So after that check, let's call this part of the code as r equal. I'm calling it AE. Let's put it in a function r equal. So check in this function, we pass P and Q. So if r equal P and Q, or rather if are not equal, then don't need to proceed further, return false. So this function will end here itself at the root level. But if they are equal, that is this condition did not hold true, then in Q1 push this 5. This is from this first root node, and this is not integer, this will be Q of tree node, or in C++ tree node pointer, like this. So both are tree node pointers. So in this case it's 5. 5 in a circle denotes a tree node structure. So Q1 has this 5, Q2 has also 5. Then here we will not just do level order traversal and not compare level by level. For example, let's say we are at some level, let's say at kth level in first tree and kth level in second tree, and here let's say we have 10, 20 as two nodes only at this level, and here we have child of 5, 6 and 7. This is at kth level in first tree, and in second tree we have again 10, 20. So if we compare at this level, you may be guessing that if we do simple BFS and compare level by level for equality, then we are good to go, but we are not good to go. Further modification is required in the BFS. So here we will see that both are same at this level, kth level. So at this level it's fine, we return true, and in fact we are true till this level. But let's say here we have 5, then we have 6 and 7. So if we simply check for this level and insert their children in the queue, so here the queue will have, after we finish with this level, the queue will have 5, 6 and 7. These will be the only 3 nodes in the queue if we are processing level order. And here in Q2 we will have 5, 6 and 7. So when we pop first element, compare with popped element of Q2, they are same. So we pop next element, that is 6, and compare, they are again same. Next we pop this node 7 and compare, they are same. So we would say that even at this level they are same, but we see that they are not same. Here this 10 has 2 children, 5 and 6. Here 10 has just one child, 5. Here 20 has one child, but here 20 has 2 childs. But if we just are concerned about a particular level, we would never discover this kind of anomaly. Maybe that below this everything is same, so it will remain as true. But we have to return false here. So what change is required? So instead of doing simple BFS, when we pop an element, we compare them. So when we pop from both Q1 and Q2. We compare if they are equal using the same logic, this function that I wrote, are equal, where we will add these logic, these 3 checks. And apart from that, we have to check one more thing. that its left child is also equal to its left child and its right child is also equal to its right child. So if 10 and 20 are in the queue, before processing kth level, we would pop 10 from both of these. So we pop 10 from first queue, 10 from second queue. They are equal, this will return true. Then we check their lefts are equal. So this will also return true. Then we will check their right are also equal. So if both are null, then that's fine, this function will return true. But here one is not null, one is null. So this will return false and our check will fail. So these are a few changes required to normal BFS. So now let's write the code for this in C++, Java and Python. So you can go through this example. These are all very simple examples. And here you see that 2 is left child, here 2 is right child. So they are different. So just structurally being same is not enough. Here also the order is changed, 2, 1, 1, 2. So they are false. Here it's exactly same. So first write the recursive and simpler solution, that is if not P and not Q, then return true. Both are null. If not P or not Q, return false. Only one of them is null. If both are not null, then we check their values. P.val not equal to Q.val, return false. Now root is valid. Its value is also same if it exists. So return So let's see if it runs. And the solution is accepted. So again it's 4 milliseconds, but if you try a few times it can be 0 millisecond as well. And what is the time complexity here? So we are traversing this tree once, both the trees. So if there are n nodes and here there are m nodes, it will be order n plus m. And what is the space complexity? We are not using any explicit space, but space will be taken by the stack that is used internally in this recursive stack. So it again can be of the order of n. So both space and time are of linear order. Now we will write the iterative way. So let's comment it out. And you must have noticed that we are checking this multiple times, this check. So we will put it in a separate function and we will call it is equal. And this will also take three nodes to compare. False and then false, else return true. So this is our is equal function. Now we will start the main code. So first we have to check for root. So we will do if not is equal P and Q. Then there is violation at the root level itself. So return false. Otherwise we will create two queues. Let's call them Q1 and Q2. And then in Q1 we will push P and this is Q1, and in Q2 we will push Q. Then P and Q are same. So we will check while Q1 is not empty. So we pick the first element from both the queues. And in C++, front just returns it. It does not pop out the element. So we need to call q1.pop and q2.pop to also pop those elements. Then we will check if is equal or rather is not equal this n1 and n2, then return false. And after checking the elements, we also check their children, and we know what is the region. So we saw the region that just checking the element which is popped from the queue is not enough. We have to also check match their children. So left with left and right with right, they should also be same. Then only we will push their left and right. Otherwise we will return from here itself. So these nodes are same, but that's not enough. We will check for their children. That is if not is equal. So better copy this one. So after checking the node, check their left. If they are not equal, return false. And this n1 can be, one of them can be null. So we need here null check. Otherwise we will get bad access. This pointer is null. So there is some shortcut here in LeetCode. You can select it and press tab, so it will shift it. If you have a long block of code like this and you want to shift it, you select it and press tab. And if you want to indent left, shift plus tab, so left. So left are same. So what we need to do, if so left can be same when both are null also. So here we add null check. q1 dot push n1 left. And similarly we have to do for right. And then we are good to go. Finally we will return true here. And this iterative approach is also accepted. So for Java and Python, I will go ahead with this recursive way. If you got this idea clear, you can try to implement it in Java and Python, whichever is your favorite programming language. It would also give you a good practice of BFS. And this solution is accepted. And here also we are, it's 0 millisecond, but still we are here. So maybe we do not have enough accepted submission. So this chart is not available, but if we are 0 millisecond, we can expect that we are right in the top region, and in fact for most people it will be in that region only. All the methods are converging to O of n. Now we will do it in Python 3. And the solution is accepted in Python as well.